Okay, so for the next part, we go on the part of how to determine the sequence is increasing, decreasing, and bounded. Okay, so here we have some terminology and definitions. Okay, we look at this one by one. So given any sequence En, we have the following. So the first one, we call the sequence to be increasing if En is lesser than An plus 1 for every n. So it means that An is smaller than An plus 1. So just assume that maybe An is 1, it is smaller than 2. Okay, so from 1 goes to 2, we know that this is increasing, right? From small number to big number. So that's why we call that the sequence to be increasing for every n. Okay, second one, we call the sequence decreasing if An is greater than An plus 1 for every n. So let's say An is bigger than An plus 1. So let's say An is 2, An plus 1 is 1. So from 2 to 1, this is actually decreasing pattern. So that's why we say that the sequence is decreasing if generally it is written this formula, En is greater than An plus 1. You can see these two logically actually. Okay, the third terminology or definition, if An is an increasing sequence or An is decreasing sequence, okay, please highlight this or. So we call it to be monotonic. So means that if the sequence is just only increasing, then it is monotonic. Or if the sequence is just decreasing, it is monotonic. But what if the case if the sequence is decreasing and increasing? Okay, means that let's say for example you have a sequence like the alternating sequence, we have -1 and then it goes to 1, -1, 1 and so on. It is alternating from -1 to 1, you know it is increasing. 1 to -1, you know it is decreasing. -1 to 1, it goes again to increasing. So in this case, the sequence is both increasing and decreasing. So this alternating sequence is not monotonic. Okay, so for monotonic sequence means that the pattern is just monotone. It is just either decreasing or increasing. Okay, so this is important because you need to know how to determine if the sequence is monotonic or not. Okay, the fourth, if there exists a number m, small m, such that the small m is lesser than the En, okay, means that this m is the terms lah, and En is another term. So this m is lesser than the En. For every n, okay, we say the sequence is bounded below. Okay, means that for the sequence, there is the smallest number for the sequence, that is the m. So this smallest number is actually the lower bound. Okay, is we call as lower bound. So means that since this sequence has the lower bound, the most smallest value, then we say that the sequence is bounded below. Okay, fifth, the other way around. If there exists a number m, big M, such that the sequence is lesser than the m, so means that the biggest number in this sequence is m, big M, for every n, and this big number I would call as the upper bound, the most biggest number or terms in the sequence, we say that the sequence is bounded above. Okay, so the number m, this should be big M, sorry, typo. So the number m is sometimes called the upper bound for the sequence. Okay, the last one, this is important. If the sequence is both bounded below and bounded above, okay, then we call the sequence to be bounded. Okay, Notice that the n, it is n, not or. So for the case of bounded, for the sequence to be bounded, it needs to be both bounded below and bounded above. If it just have the upper bound, if it just bounded below only, or if it just bounded above only, but not both side, then the sequence is not bounded. So for the sequence to be bounded, it needs to have both upper bound and lower bound. It needs to be both bounded below and bounded above. So it is different for the case of monotonic. Okay, this is the important terminology and definitions you need to know lah. Okay, so let us look at example 3. Okay, example 3, determine if the following sequence are monotonic and or bounded. Okay, so how can we determine the sequence is monotonic and bounded? So let us look at example 3. Okay, you are actually provided the solution. You can read the solution, but this solution actually gives you the way how you can recognize by thinking logically. But then I would give you another way for you to determine. Okay, let us do example 3 together. Okay, example 3A. Negative n square so n from 0 to infinity. Okay, we want to check if it is monotonic, is it bounded. Okay, for monotonic, for you to know, you need to check if the sequence is increasing or decreasing. Okay, we go one by one. We check first on the increasing or decreasing. Okay, for this one, you actually need to recall back from calculus 1. Okay, how can you check if the function is increasing or decreasing? So the same thing we apply here, but this is for the case of sequence. So what you can do is that we try to imagine this sequence to be a function. So I let the sequence to be a function, so I let it to be fx equals to negative x square. So this depends on the sequence lah. Sequence we have negative n square, so if we convert it to be a function, I put it as negative x square. So I consider x lah instead of n. Okay, so we adapt the idea of finding the increasing or decreasing of a function towards this sequence. But of course, at the end later, you need to come back to recognize back that this is regarding the sequence, not the function. So always be proper in your conclusion later. But this is just the method or the way before we come up with the conclusion. So we take the idea from recognizing the increasing or decreasing pattern from the function. Okay, so recall back on how can you determine decreasing or increasing of the function. So if you recall back from calculus 1, for you to determine this, you need to consider the first derivative test. Okay, still remember the application of differentiation. We consider the first derivative test. Okay, that is if you find the first derivative of the function is positive. Okay, and then we say that the function is increasing. Okay, and then if you find that the first derivative is negative, then the function is decreasing. Okay, of course, this provided with that x is within some interval lah. Okay, so in this case, n starts from 0 to infinity. So I would write as x has the interval from 0 to infinity. Okay, so let us check this one. we find the first derivative for the function first. So the first derivative for the function negative x squared, so you differentiate this one, you would get it negative 2x. Okay, so now you get negative 2x. So you know this x is in between 0 to infinity. So we try to plug in any number inside this interval into the first derivative. So let's say I choose I choose the x. I choose any number inside the interval. I choose like 1. So you plug in, if fx is 1, then you get it is negative 2 multiplied by 1, then it is negative 2. You can check for any number inside this interval. Okay, so I just put 1 because it is much easier. So you get the first derivative when x is 1 or whatever number inside the interval, you get a negative number. So this is actually decreasing. Okay, so for the case of function, we can say that the function is decreasing. Now we come back to the sequence. Okay, so we can conclude here. Okay, therefore the sequence negative n square is decreasing. So it is decreasing at x from 0 to infinity, right? Okay, so means that hence the sequence is monotonic. Okay, another thing that you need to notice about this is that if you recall back calculus 1, before you recognizing the increasing of the function, you need to recognize what is the consider interval. Okay, to know the consider interval like this, it is given to you, it is from 0 to infinity, right? But another way for you to consider the interval is that you need to find is there critical point for the function. Okay, because we would consider the interval based on the critical point. So for example, like let's say like this, if you try to find the critical point, is there any critical point for this function? So critical point, how to find critical point? It is the first derivative you equate equals to 0, or the first derivative does not exist. So you try to find what is the x. X is the critical point from this condition. So in this case, if you equate the first derivative, that is negative 2x. Okay, negative 2x equals to 0, then you get that the x equals to 0. So x equals to 0 is the critical point for the function, or you can equate to b does not exist. So in this case, this function is always exist lah, so it doesn't applicable to the second condition. So x equals to 0 is the critical point. Okay, but then it doesn't matter because this interval for the sequence starts from 0 to infinity. So in this case, you would say that within this interval, the function will always be decreasing. Okay, but then let's say you have a critical point, maybe for another kind of functions or sequence, maybe you get the critical point to be 2. Okay, just example. So you need, and the interval for the x is from 0 to infinity. So what you need to do to recognize, to determine the increasing or decreasing function, first you need to separate the interval, because x equals to 2 is the critical point. So means you need to check the first derivative at the interval of 0 to 2 and at the interval of 2 to infinity. Okay, it is not a problem if you find that within this interval the pattern is the same. For example, if this is increasing, this is also increasing, or this is decreasing, and this is increasing. So it is still monotonic. But what if you find out that this part is decreasing, but this part is increasing? Okay, then it is not monotonic. But for this case, since the critical point is at 0 to the rest, it doesn't cut it doesn't cut the interval, then there is no problem. So we can say that the sequence is just decreasing within this interval. Hence, it is only decreasing, hence it is monotonic. Okay, because later you will see there is an example that has the critical points. Okay, we go to the just the easy parts first. Okay, this is for the monotonic. So this sequence is monotonic. Okay, second one, we determine, is it the sequence is bounded? So to say that the sequence is bounded, it should have the lower bound and the upper bound. So it means that you need to know the first term and the last term. So to know the last term, we know that the sequence starts with maybe it starts with 0, it can start with also 1, and it should end with a very very big number as n goes to infinity. So thus, for the case when n goes to infinity, thus it gives you a finite number. Okay, if it gives you a finite number, which is the limit, then it has the bound lah for the last term. Okay, so let us find if this sequence is bounded or not. Okay, to check the boundedness. Okay, the first thing that we can do to check the boundedness is we can always try to expand the sequence. Okay, if you try to expand the sequence for just a few terms, okay, starts with n equals to 0. So if negative 0 square, we get 0. Okay, if n equals to 1, so negative 1 square is negative 1. If n is 2, we get negative 2 square, we get negative 4. If n is 3, we get negative 9, and so on, dot 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 until infinity. So if you look at this sequence, it goes from 0 to negative 1, negative 4, and negative 9. And also you have checked that this sequence is decreasing, and which also means that it is monotonic. So you compare between this term, the smallest term here is, you don't know because it goes from big number to the small number. So the smallest number would be somewhere here when n goes to infinity. But then you can say that the biggest number here is 0. So 0 is actually the upper bound because this is the big number inside this sequence. So when it has the upper bound, means that the sequence is bounded above. Okay, so you fulfill one of the condition for it to be bounded. It is bounded above. But then you need to check, is it does it have the lower bound? So to check the lower bound, it is for the case when n goes to infinity. So when you know that this is for the case n goes to infinity, what you need to do is you need to apply the limit. You need to find the limit. So let us find the limit for negative n square, the limit of the sequence. So the limit as n approaches to infinity for negative n square. Okay, first thing first, you can plug in the value of n as infinity to find the limit. So you would get negative infinity. So negative infinity, infinity is not the indeterminate form. So this is it. You cannot adjust the negative n square. So this is it. This is infinite. Okay, recall back, if it is infinite, then it is divergent sequence. Okay, so means the terms as n goes to infinity, it goes to a very very small number. It goes forever to a very small number. So means that it is not bounded. It doesn't stop. The sequence doesn't stop. It goes forever to a very very small number. So means that this sequence doesn't have lower bound. Okay, so means that hence it is not bounded below. Okay, so you might want to conclude the sequence is bounded above by 0 but doesn't have lower bound, which is it is not bounded below, hence the sequence is not bounded. Okay, not bounded because it doesn't both bounded above and bounded below, so it is not bounded. So for this sequence, for this example, the sequence is monotonic but not bounded. Okay, this is for example 3A. Okay, let us do 3B. Okay, for 3B, you have example is -1 to the power of n plus 1 and from 1 to infinity. Okay, so first thing first, let us try to just expand it on a few terms. So if you try to expand, start with n equals to 1. So -1 to the power of 1 plus 1 is -1 square. -1 square is 1. Okay. When n equals to 2, then -1 to the power of 2 plus 1 is -1 to the power of 3. So it is -1. And if we find the third one, it is come back to 1, then -1, and so on. Okay, so you can see that this sequence is the alternating sequence. So if you try, maybe if you want to just to illustrate, the graph for this sequence is it goes from -1 to 1. So it starts with 1. Let's say this is 1 lah. Sorry, this is n, this is en. So it starts from 1 and then 2, it goes to -1 and then 1, -1, 1, -1 until so on lah. So it is alternating. So from here you can actually see it is actually clearly bounded by 1 and -1. So it just goes in between 1 and -1 and so on. It doesn't goes to any other value. So here we can say that directly we can say that this sequence is bounded above by 1 because 1 is greater than -1, and it is bounded below by -1. Okay, by just illustrating this, you can actually logically find the answer whether it is bounded or not. So okay, and also another thing from this illustration, you can also recognize that this sequence is actually not monotonic. Because why? It goes from positive to negative, which is decreasing, and then it goes to negative to positive, increasing, and then it goes to decreasing, increasing, and so on. So it is both increasing and decreasing. So therefore it is also not monotonic. Okay, you can see it clearly. But we can from this we can conclude that the sequence is alternating sequence. Okay, hence it is not monotonic. If the sequence is alternating, then it is not monotonic. Okay, this is for the case of monotonic. And for the case of boundedness, for the case of bounded, okay, okay, you can see it clearly. As I said previously, you know it is bounded above by 1 and bounded below by -1. But let's say if you want to try to find by using the limit, we can try to find it. Okay, let us try to show the proof or the steps of the boundedness by using the concept of limit. So let's say you find the limit as n approaches to infinity for the sequence -1 and +1. Okay, okay, first thing first, we can directly plug in the n as infinity. So you would actually get -1 to the power of infinity. Okay, so since it is, if you put any value, okay, since you have tried to illustrate it, it can goes either -1 or 1. Okay, if you put a very big value for the power that is infinity, it could be either actually -1 or 1. It depends. If it is infinitely odd number, then it gives you -1. But if the infinity is even, then it gives you 1. Okay, so in this case, it doesn't approach to one number. Okay, so therefore we can say that the limit does not exist. Okay, because it keeps bouncing. From -1 to 1 and so on lah, till forever, which is alternating lah. Okay, we don't get the the last point. We do not know what is the very last point. It is either -1 or 1 until forever. So we can conclude that the sequence is bounded above by 1. Okay, because based on this sequence we expand, the biggest number is 1, the lowest number is -1, and bounded below by -1. Hence, since it is both bounded below and above, hence the sequence is bounded. Okay, so for this sequence B, it is not monotonic, but it is bounded. Okay, this is for B. Okay, let us go to C. So C, the sequence given is 2 over n square, and from 5 to infinity. So we want to check the monotonic. Is it monotonic? Okay, so you might want to maybe try to expand it for a few terms maybe. So the first term, it starts with n equals to 5, then you get 2 over 25, then you get 2 over 36, 2 over 49, and so on. Or I can write it in decimal because it is easier for you to recognize which one is bigger, which one is smaller. One and dot dot dot. Okay, so from this, at first glance, it starts with 0.08 and then it goes to 0.056. So between these two, it is decreasing. This is also decreasing. So somehow you have the idea that this sequence is decreasing, but we need to check it again. And also you can also recognize, based on these three terms, you can recognize that the largest one is 0.08. So this somehow could be the upper bound, just to get the idea before we start finding the exact method, the exact way of finding it. So this somehow could be the upper bound. So it is bounded above. Okay, let us check it thoroughly to check for the monotonic. So first, like previous one, we consider the limit to become a function. So I write as fx equals to 2 over x squared. So you find the first derivative. So the first derivative is negative 4 over x cubed. And note that the x is having interval from 5 to infinity. Okay, based on what is given, and from 5 to infinity. Okay, okay, you may want to check if there is a critical point for this function. So to check critical point, I let for the fx, the first derivative, negative 4 x cubed equals to 0. So from this one, you don't get any solution. Okay, and then second condition, you can check if the function does not exist. So the function does not exist. For the case of negative 4 over x cubed to be does not exist, it should be that the x cubed should be 0. So means that x is 0. But if you check that x equals to 0 is not within the interval, so it is okay, because the critical point is not inside the interval, because our interval is just from 5 to infinity. Okay, so you can directly find if the function is increasing or decreasing. So we have this first derivative. We try to plug in whatever value within this interval inside the first derivative. So let's say I choose 6. Okay, then you get negative 4 over 216. So negative 4 over 216 is a negative number. So therefore this function is decreasing. Okay, so in terms of function, it is decreasing. So it applies the same for the sequence. So you can conclude that the sequence is decreasing only. Okay, hence it is monotonic. Okay, that is for the monotonicity. And then we check on the boundedness. Okay, previously as you expand, you have the idea that you know it is decreasing. You have the idea this could be the upper bound. Alright, so means that it is bounded above. So let us find, is it bounded below? Because you know it is a decreasing, so it should have it getting smaller and smaller. So does it have the end value, the last value, or is it have the lower bound? So to know the lower bound, it is for the case when n goes to infinity. Because we know that the sequence starts from 5 to infinity, so we find the limit n approaches to infinity for 2 over n square. Okay, this one you can directly plug in the value of n as infinity. So 2 divided by infinity, you get 0. So 0 is a finite number. Therefore, you can say this sequence is also convergent, or converge to 0, sorry. And it is also a convergent series. And you know that the last term is 0 and goes to infinity. So means that this sequence is bounded below. Okay, so we can conclude the sequence is bounded above by, okay, berapa tu? 0.08, or I write it as 2 over 25. Much more correct lah, or exact, because it has a decimal 2 over 25. So the sequence is bounded above by 2 over 25 and bounded below by, so the last term it goes to 0, bounded below by 0. Hence, the sequence is bounded. Okay, and that things we can conclude that the sequence has limit of 0 and the sequence is also convergent sequence. Okay, this is for C. So let us go to okay, last example for this example 3, D. So D, we have sequence cos n pi over 2 and starts from 0 to infinity. So this involving trigonometry, involving cos. So let's say you want to try to expand it first to a few terms. Okay, so when n equals to 0, which means we have cos 0 is 1. Okay, and then when n equals to 1, we have cos pi over 2. Pi over 2 is cos 90, you would get 0. And then n equals to 3, you get cos 3 over 2 pi, you get negative 1. Okay, you can use your calculator to find this. And then when n is 4, you get cos 2 pi, cos 360 is 0. And if you find out the rest, it goes to 1 back, and then 0, and then negative 1, and so on. So if you want to try to illustrate this in terms of graph, it looks like this. This is n, this is an. So first, second, okay, it has also negative parts. So the other 1, negative 1 and 0. So the first term when n equals to 1, it is 1. Second term, it is 0. Third term, negative 1, and then it goes back to 0, and then to 1, and then 0, and then negative 1. So you can see the pattern, it is alternating from 1 to negative 1. In between is 0 lah. So 1, negative 1, 1, negative 1, and so on. So you can recognize it at the first glance, it is alternating sequence. So again, alternating sequence is not monotonic because it has both decreasing and increasing. So you can conclude that the sequence is alternating, hence alternating sequence, hence it is not monotonic. Okay, not monotonic. Okay, how about the boundedness? So if you look at this graph, the value for the an is just either 1, 0, or negative 1. So the highest value, it just the area would just be negative 1 and negative 1. So the highest value between these two is 1, and the lowest value is negative 1. So you know it is bounded above by 1, bounded below by negative 1. So 1 is upper bound, negative 1 is the lower bound. So you can conclude again the sequence is bounded above by 1 and bounded below by negative 1. Okay, so this is the answer. So hence the sequence is bounded. Okay, so means that for this sequence, it is not monotonic, but it is bounded. So if you notice that the way we try to determine if it is increasing, if it is monotonic or bounded, we can consider to try to expand the sequence. and we can try to illustrate and to think logically, and we can also consider the first derivative test. We let the sequence to be a function, and then we can also use the concept of limits. Okay, so that is the way. It depends on the types of the sequence. So the way for us to recognize this, it depends on the types of the sequence. So you might also want to look at the given solution. You try to relate, but the given solution is more on giving you the logical reasoning on how we can recognize it. So please just read the way it is explained to you on this solution. Okay. Okay, so please just read this as well and try to relate with what you have. Try to show whether it is monotonic or bounded. Okay, next we go to example 4. Example 4, determine if the sequence is monotonic and bounded. So the same thing. So let us try to do this one. You can also try to read the solution, but let us do it together using the other comprehensive way. But actually I think it is the same. Okay, we do it together again. So example 4, we have sequence n over n plus 1 and starts with 1 to infinity. So you want to check again the monotonicity. We apply the same concept as previous. We apply the same method as previous. So the first steps, you might want to just expand the sequence for a few terms. So when n equals to 1, the first term, we would get the first term is 1 over 2. When n equals to 2, we get 2 over 3. N equals to 3, we get 3 over 4, and so on. Okay, I can write it into a decimal. 1 over 2 is 0.5. 2 over 3 is 0.667. Of course, I run off this one because it has a lot of decimal. 3 over 4 is 0.75, and so on until infinity, but we do not know it has a limit or not. So if you look at this pattern of the sequence, you can recognize this is actually increasing. It goes from small value to the high value. Okay, so in this case, the small value based on these three first terms is 0.5. The smallest value is 0.5. So somehow, in this case, you have the idea that somehow maybe this 0.5 is the lower bound, and maybe it is bounded below by 0.5. Okay, but we need to confirm, is it true? Okay, so to confirm, we let the sequence to be a function first. So I let fx equals to x over x plus 1. Okay, and then we find the first derivative. First derivative, you use the quotient rule, recall back calculus 1. So we have differentiate x, multiply by x plus 1. Differentiate x is 1, then you have only x plus 1 minus x. Differentiate x plus 1, you also get 1. So just x plus 1 minus x divided by x plus 1 square. So this can be simplified. X minus x is 0. So you just have 1 over x plus 1 square. Okay, so this is the first derivative. So maybe you want to check, does it have critical point for this function? So just check, no harm to check the critical point. That is for the case you can check on two conditions: first derivative equal to 0, or the first derivative does not exist. So in this case, it is applicable for the case it does not exist. So this first derivative does not exist if the denominator is equals to 0. So I equate it to be 0. So we get that x plus 1 equals to 0. So x is negative 1. So in this case, the critical point for the function is x negative 1. But this critical point is not applicable for this function because this function, we see that this sequence starts from 1 to infinity. Okay, n is a natural number. It should always be a positive number. So it doesn't affected by this critical point because we just want to check for the case of x in the interval of 1 to infinity. So it doesn't have a problem with this x equals to negative 1 as the critical point. Okay, so we can further proceed. to find the first derivative, check the first derivative within this interval. So I plug in any value within this interval. So let's say you can plug in any value. Let's say you plug in 2. Okay, so 2 divided by 2 plus 1, you get a positive number. So positive number means that if the first derivative is a positive number, then means that it is increasing. The function is increasing on the interval of x from 1 to infinity. Okay, so since the function, in terms of function, it is increasing within that interval, so we can conclude, we go back to the idea of sequence. So then we can conclude that the sequence is also increasing from n1 to infinity. The sequence is increasing, hence it is monotonic. Okay, that is for the case of monotonic, to check the monotonic. And then we go to check the boundedness. Okay, this is to check monotonic. Okay, and then we check the boundedness. Okay, so look back at this expansion for the sequence. You have the idea, you know that now it is confirmed to be increasing and it is monotonic. You know that it goes from big number to smaller number as the end approaches to infinity. So you know that this 0.5 is confirmed to be the lower bound. So it is, the sequence has been proven to be bounded below. Okay, so now we want to check if it is bounded above or not. So to check if it is bounded above or not, we check the limit n goes to infinity. So limit n goes to infinity for n over n plus 1. Okay, so now you can actually apply, okay, so let's say just plug in first the n as infinity, you would get infinity over infinity, which is indeterminate form. So you need to adjust. So let's say, okay, we consider the, we factor the n, we consider the factor method. So limit n goes to infinity, we factor n outside for the numerator and denominator. So we get n multiplied by 1 divided by n multiplied by 1 plus 1 over n. Okay, so you can cancel out the n. So what you get is limit n goes to infinity, 1 over 1 plus 1 over n. So you plug in n as infinity, so this part you get 0. So what's left is 1 divided by 1 plus 0 is just 1. So you have the limit. You have the finite limit. The limit is finite, and you can also conclude that the sequence is convergent. Okay, this is one way, one option of the way, or you might want to apply the L'Hopital's rule. You can choose either one, it's up to you, but I just show it both. If you apply the L'Hopital's rule, means that you differentiate the numerator or denominator. So you differentiate, okay, or you can write in terms of x, because the L'Hopital's rule is applicable for a function. So you can write in terms of x. So x goes to infinity, x over x plus 1. Okay, we apply the L'Hopital's rules, means that we differentiate numerator and denominator. It becomes, differentiate x, it becomes 1, differentiate x plus 1, it also becomes 1. So the answer is the same, you get 1. Okay, so 1 is a finite number, then you know that 1 is the upper bound. So means that it has a value for the first term and it has a value for the last term. The last term is not infinity. So here you can conclude that the sequence is bounded below by 0.5 or 1.2 and bounded above by 1. So hence the sequence is bounded. Okay, so please always remember bounded below is for the case is for the terms that is the most smallest. Bounded above is for the terms that is the most biggest. Okay, below and above. Okay, so in this case, for this example, the sequence is monotonic and it is also bounded. Okay, you might want to make a proper conclusion here again. So the sequence is monotonic and bounded. Okay, this is important to make a conclusion based on what you have determined. Okay, we go on we have another theorem, theorem 1.5. If an is bounded and monotonic, if it is both bounded and monotonic, then the sequence is convergent. Okay, like the previous example, it is monotonic and it is bounded, then it is convergent. So you have proven that it is convergent because the limit is 1, it is a finite limit, then it is convergent. Okay, however, note that this theorem 1.5 does not say that if a sequence is not bounded and or not monotonic, that it is divergent. Okay, this is correct this way, but the other way around, it doesn't necessarily applicable. Okay, so let us look at example 5. This is actually the last example. We have a bit of complicated sequence. Okay, we want to check, is it monotonic and or bounded? Okay, let us do this. Okay, I wrote this already here, but you can always try to read the solution, of course, but I just want to show you the steps. Okay, example 5. So we have sequence n cube over n to the power of 4 plus 10,000. So the limit starts as at n equals to 0 to infinity. Okay, so we want to check the monotonicity. Okay, so again, you might want to express or expand this sequence. So if you try to expand this sequence, okay, we just refer this one lah. Okay, if you try to expand, the first term would be this one, this is the second term, third term, and so on. If you look at this, the difference between A1 and A2, it is increasing, A2 and A3 increasing as well, A3 to A4 increasing, and so on. You can see that from the first term to the 10th term, it is increasing. But does it true? Okay, so you need to confirm that. So to confirm this, we apply the concept of the decreasing or increasing of the function. So we let the sequence to be function for a while. So fx equals to x cubed over x to the power 4 plus 10,000. Okay, so you find first the first derivative. Apply the quotient rule. So the quotient rule, I hope you know how to do it. Okay, but then I show you lah. Okay, so x cube, we differentiate x cube, multiply by the denominator, then you have 3x square. Denominator is x to the power 4 plus 10,000 minus x cube, and then multiply with the derivative of x4 plus 10,000, then you get 4x cube. Okay, divide by x to the power 4 plus 10,000 square. Okay, don't forget to square. Okay, so in this form, you can actually try to simplify it. So I want to factor x square outside, so it becomes x square 3x4 plus 30,000. Okay, this one I want to factorize just x cube, not x, I want to factorize x square, not x cube, so minus x square, then it becomes 4x4. Okay, divide by x to the power 4 plus 10,000 square. So the numerator you can simplify. So since we have x square for both part, then x square I put it outside. So x square 3x4 plus 30,000 minus 4x4 divided by x4 plus 10,000 square. Okay, so this one you can simplify 3x4 minus 4x4. Then you would get negative x4 plus 30,000. Okay, divide by x4 plus 10,000 square. So just to rewrite it back, I don't want this x4 to have minus here, so I put the minus outside, so it becomes minus x square x to the power 4 minus 30,000. Okay, divide by x to the power 4 plus 10,000 square. Okay, so this is the first derivative. Okay, okay, and you know this is the interval for the x we consider here. It starts from n0 to infinity, so we somehow consider the interval for the x to be from 0 to infinity. Okay, okay, just to be careful, we need to check first, does this function has a critical point? Because when there is a critical point, we might need to check the decreasing or increasing based on that critical point. We want to check the interval for increasing or decreasing based on the critical point, because it somehow might be different, depends on the interval. Okay, so just to be confirmed, just to be careful, we first try to check the critical point. Okay, so the first derivative to check for the critical point, we equate it equals to 0 first. So if we equate this first derivative equals to 0, then we get x square x4 minus 30,000 divided by x4 plus 10,000 square equals to 0. So if you equate equals to 0, then we bring this here, you get a 0 lah. So it becomes negative x square x to the power 4 minus 30,000 equals to 0. Okay, so you find what is the value of x when it is equated to 0. So the first one, you can find that negative x square equals to 0. So x is equals to 0. Second one is, so this is the first critical point. Second one is x to the power 4 minus 30,000 equals to 0. So you get x to the power 4 equals to 30,000. So what is x? So you find x is actually, you can use your calculator, it is actually plus minus 13.16074. Okay, but you need to remember, this is for the case of function. But in our case of a sequence, the n should be integer. So we know that this x is actually, it comes back to the n lah if it is a sequence. So we only consider for the case of x when it is integer. So when we round off, this one x should be approximately equals to plus minus 13. Okay, I wrote it back one by one lah. It is approximately becomes negative 13 and 13. Okay, so we have this critical point x0, negative 13 and 13. Okay, but you need to notice back, you need to check back. Okay, in our sequence, it starts from 0 to infinity. Okay, so our x here critical point is 0, negative 13 and 13. So this x is actually the n if we come back to the sequence. So means that this negative 13 is, this negative 13 is not applicable in terms of n. Okay, because n should be a natural number, it should be positive integer. So we exclude this x negative 13. Okay, but then we still consider 0 and 13 because it is within the value of the n. Okay, so this is considered, and 13 is also considered. Okay, so this is the critical point. Okay, so recall back for calculus 1, for you to check the increasing or decreasing, it depends on the critical point, right? So we have critical point x equals to 0, x equals to 13. This is the critical point. Okay, so you need to find, you need to check the first derivative within this interval based on the critical point. Okay, so it starts with 0. We doesn't consider the negative part, so this part is tak ada lah. Okay, so it goes to, so we need to check for x 0 to 13 and 13 to infinity. Okay, so you plug in any value within this interval for inside the first derivative. So if you try to plug in any value, you can try this one. You would get here the first derivative would be a positive number, and this one you would get the first derivative is negative number. So means that at this interval 0 to 13 it is increasing, and at 13 to infinity it is decreasing. Okay, so means that at the turning point or the critical point x equals to 13, the pattern is changing from increasing to decreasing. So we come back again to the sequence. Okay, in terms of sequence, it is also the same. So means that at n equals to 0 to n equals to 13, the sequence is increasing. Okay, and when n equals to 13 to n goes to infinity, the sequence is decreasing. So since we have both for this sequence, okay, this is in terms of sequence. So since we have both for this sequence, increasing and decreasing, therefore we can conclude that the sequence is not monotonic. It is not monotone. The pattern is not monotone. So it is not monotonic. Okay. And then we go to check on the boundedness. Okay, in this case, to check on the boundedness, we also need to consider the idea from the critical point that we find. Okay, that is, we need to check for the case n equals to 0, the starting point, and then we need to check at n equals to 13, okay, this part, and then we need to check n equals to infinity, or goes to infinity lah, okay, this part. So 0, 13, and n goes to infinity. Okay, we need to check at this point, okay, to determine the boundedness. So when n equals to 0, you would check that the sequence E naught would becomes 0.000099 ... because the decimal is a lot. Okay, and then at E13, at the 13 terms, it gives you 0.056975. Okay, and when E is infinity, it gives you what value? So to know for the n goes to infinity, we need to consider, we need to find the limit. So we find the limit of the sequence n goes to infinity. So the sequence is n cubed over n to the power of 4 plus 10,000. Okay, so if you directly plug in the infinity inside the n, you would get indeterminate form, infinity over infinity. So we need to make adjustment. So okay, maybe we can apply the L'Hopital's rule. So I apply L'Hopital's rule. L'Hopital's rule is actually applicable to a function, but I think it doesn't be a problem lah if you consider the symbol of n. So let's say I apply, so limit n goes to infinity, we differentiate the numerator and cube, it becomes 3n square, and then the denominator it becomes 4n cube. Okay, so this one you can simplify. So you can simplify, you can cancel out, this becomes limit n goes to infinity 3 over 4n. Okay, and if you plug in the n as infinity here, you would get 3 divided by infinity. So 3 divided by infinity, 0. So 0 is a finite number. So you can also conclude that the sequence is convergent because the limit is finite number. Okay, we come back to find the boundedness. So a infinity, which is the limit, you get 0. Okay, so based on these three terms, look at these three terms. Which one is the most smallest? Which one is the most biggest? So the most smallest is 0. Then this is the lower bound. So means that the sequence is bounded below by 0. And the biggest is 0.056975 and so on. So this is the upper bound. So the sequence is bounded above by 0.056975. Okay, so you can conclude now. So the sequence is bounded above by 0.056975. This is for the A13, and bounded below by 0. Okay, hence the sequence is bounded. Okay, so for this sequence, it is bounded and it is monotonic. So you might want to check the solutions given here. Is it the same? Oh, sorry, it is not monotonic. Okay, we found out it is not monotonic previously. Okay, so it is bounded and not monotonic. Not monotonic and bounded. Okay, so it is correct as what has been provided by this solution. Not monotonic, but it is convergent. And it is also, okay, where does it sit? It is not bounded. Okay, it's okay. It doesn't mention here, but we have proven that it is bounded. Okay, so this is the way on how you want to determine if the sequence is monotonic and or bounded. Okay, okay, what else I need to show you? Okay, so since this sequence, we found out that it is not monotonic and bounded. So the things that it says here that this theorem does not say that if a sequence is not bounded and not monotonic, that it is divergent, because in this case we found out that it is also convergent. Okay, though it is not monotonic but it is bounded, it is also convergent. Okay, so it doesn't necessarily say that this theorem is otherwise of this theorem is divergent lah. Okay, because we found out for this sequence it is not monotonic, it is bounded, but it is still convergent, it is not divergent. Okay, so I think that's all for this chapter 1. So if you have any curiosity or if you have any questions regarding what I have explained in this video, please feel free to list out to me all those curiousness and all those questions. So I will try to answer on Thursday, on our online class on Thursday, and we will discuss all the your curiosity, or if you have any questions, and maybe I will give you some of questions for your exercise. Okay, so I think that's all for this chapter 1. We have completed the chapter 1, which is about sequence. So the next chapter 2, it is about series. Okay, different things to sequence. You would see what is the difference. Okay, so that's all from me for this chapter 1, and thank you very much. Okay.